So if you are going to have any concurrent data accesses on your buffer or on any of these data types that we are going to talk about today, you need to basically lock your data. And that goes without saying basically, but I'm just reminding you. So let's switch to queues. And queues are basically a very simple data structure where you have from one side enqueuing an enqueuing function that puts data in the queue, and the queuing function from the other side that basically pulls the data from the queue. And this is called the first in first out queue. So you basically have the data coming in, uh, you have the data coming in from the enqueue side and the data being dequeued from, well, the dequeue side. You can have what is called a LIFO queue, and a LIFO queue is basically a stack. And in a stack, you will have enqueuing from one side, but you will be dequeuing also from the same side, and that's basically a stack. So Linux provides you with a K FIFO, a queue with first in first out semantics, and it's called kernel first in first out basically. And the implementation is slash include slash Linux slash K FIFO.h. And you basically have a struct K FIFO that defines well, some things about how the queue will look like. So in the sorry, in, out, mask, size, and a pointer to the data. Let's look at how you actually insert things into the queue. You use a K FIFO in function, and that's for enqueuing, and you use a K FIFO out function for dequeuing. So to create a queue, you use K FIFO alloc. This is one way. There are two ways to create K FIFO queue, and the first one is basically using a function that's called K FIFO alloc. And K FIFO alloc dynamically allocates a new FIFO buffer. You basically start by you have three parameters to add. The first one is a pointer to the FIFO, where I mean, well, where will your K FIFO be? The second one is the size, the number of elements in the FIFO, and this must be a power of 2 because computers are, well, they like a power of 2, so you cannot have 35 here, for example. And then you pass what is called get free pages mask, and this is something that you pass to kmalloc. We'll talk about this hopefully very soon. And then a queue will be created and initialized. A K FIFO queue will be created and initialized with the size that you have basically designated. Upon success, K FIFO alloc returns 0, and if an error occurs, you return a negative error code. This is a very simple example to start to initiate a K FIFO queue. So you basically define a struct K FIFO FIFO, and you have to of course include K FIFO.h before that, because that's where K FIFO is actually defined. So you basically include the K FIFO, and then you initialize an integer for the return code, and then you basically try to allocate the memory using the pointer to the K FIFO that you're trying to work with, page size, and GPF kernel, and we'll talk about this later. And well, this should be that. This should be FIFO basically. It should not be KIFO. Okay. So the second way to initialize a K FIFO queue is using K FIFO init, and this actually returns void. And you basically supply a K FIFO queue again, a pointer to it. You supply a buffer size, and you supply an unsigned int size. The function creates an initialized K FIFO that will basically have the size of bytes of memory pointed at by the buffer for its queue. Okay, so this will be your size, and this will be your pointer. And the size must be a power of 2 basically. For enqueuing, you can use well, you have to use K FIFO in, and K FIFO in takes as input the queue that the queue that you're trying to basically push things into. It takes a point constant void from, and that basically starts from where you're going to enqueue data, and the length of the data that you're going to enqueue. Uh, and this is from where you're going to enqueue data, right? So this copies the lem bytes starting at from into the queue represented by len. So you have some place where you have data, and that's basically your from. And you are going to copy this number of bytes into the K5O. This can be a pointer. I mean, if you're, for example, working with your project, this will be the place from which you're trying to copy the data into the FIFO queue. Okay, so this is where your data resides, and you push it there basically. On success, you get the number of bytes that have been queued, because the queue has a predefined size, and if you try to go beyond that, you will not be able to. So on success, you get the number of bytes that were enqueued. If you get a 0, that basically means that you have been able to enqueue 0 bytes from the data, and then you might want to loop, you might want to basically wait, you might want to sleep, you might want to do something basically based on your application. Suppose that, and basically if you copy half your data, then you know that you have copied half your data. You might have you might basically stop and start copying data later. For the queuing, you use K5 out, and that basically looks like this. So you again have a place that you're going to copy the data to, and the amount of data that you're going to dequeue from your K5O, and the K5O that you're going to dequeue from. You can peek at the data without dequeuing it, so you can basically get the data while not dequeuing it, and then you can use K5O out peek, which does exactly that. And in that case, you're not going to basically change anything in the queue. You're just going to read that amount of data and have it so that you basically know where the data is, and your data will again be in 2. And basically the out offset is not incremented. It's basically a way to just take a look at the data without having anything changed in the queue, and then a subsequent call to K5 out will just return you the data.